Well, greetings, mathletes, and welcome to attempt number 2 of estimating area with rectangles. Um, yeah, I apologize about the last video. One of two things happened. Either I accidentally turned off the mic somewhere along the line before I started the video, or when I updated my recording software, it changed a setting. I'm not sure which, but yeah, there was no sound. That was incredibly frustrating. I'm laughing now, but if you'd seen me a couple days ago, I wasn't laughing too much about it. I'd spent a lot of time on that video. So, in any case, let's go ahead and continue. Kind of dust it off and head through it one more time. Okay, so we are going to be estimating areas underneath curves with rectangles. So let's take a look at what that actually means. Okay, so let's say we have some function, right? And I'm only gonna look at positive values right now, so we can play around with it a little bit. So this is our f of x, and we want to estimate the area under the curve between 2 points on this curve, a and b, right? And so a is going to be your lower value, and b is going to be your upper value. Okay, now we're just going to talk about what we're doing theoretically here. The idea is that if you can carve out a bunch of little rectangles in here, let's change the color. Right, if you can fit a bunch of little rectangles in here, you could find the area of each of these rectangles. Each one has a length and a width. And if you multiply the length and the width, you get an area. And then you can add up all the individual rectangles. And, oh, I did that one wrong. That should have been here. You can add up all the areas of all those individual rectangles and get an estimate of the area underneath the curve, right? The more rectangles you have, the better the estimate, right? That's the idea. Okay, so let's take a look at one of these rectangles. If I'm looking at this, how do I want to do this? I'm just going to pick one rectangle. How about this one? Well, it's not a perfect rectangle, but you'll notice what we've done is the height of the rectangle is a function value, right? So f of x tells you how far above the x-axis you are, sometimes how far below the x-axis you are. But the height of this rectangle, each one of these individual rectangles can be found if, I'm just going to call it, I'll call it xi, right? Just because we're going to have subscripts on the x's. If this x value is xi, then the height of this rectangle is f of xi. Right? Now, if you want to find the width, well, it's a matter, it depends on how many rectangles you've chosen, right? So if n equals the number of rectangles, right, then all we have to do is take this length right here, however long the whole thing is, and just divide it into the number of rectangles we have, and that will tell us the width of one rectangle, right? You can actually figure out how big one rectangle is by looking at that. So the length of the entire interval where you're finding the area is b minus a. Well, if you want to figure out the width of the rectangle, you divide by the number of rectangles you have. That's n. Now, we denote the width of a rectangle is equal to delta x. Now, if you've probably come across the delta before, it's the Greek letter delta. It looks like a triangle. It's an analog to the English letter D, which is more familiar to us. It stands for difference, but that delta means a change in something. So really what it's talking about is how much x changes from one side of the rectangle to the other. So b minus a over n is your delta x, right? That's the width of the rectangle. In fact, that's the width of every rectangle is your delta x. So what we need to find are all the x values where we're going to evaluate the function so that we can figure out all the individual heights. And then we'll multiply each one of those by the delta x. And so that's the length times the width of a rectangle. And then we add everybody up. Sadly, this becomes a very tedious section. You're going to be doing some arithmetic as you go through this, and you'll see as we look at our first example. So I've kind of I've done this big arm sweeping general description of what we're going to do. Let's go ahead and actually get in here and get our hands dirty now. Okay. So let's suppose we're given a function, and let's pick something that we're familiar with. Let's say it's x squared plus 1, which is a parabola that's been shifted up by 1 unit, right? And we're going to try to find, we're going to estimate the area on the interval from 0 to 2. Now, I just want to point out, we're actually going to go through this 3 ways. So let's say this is a function. I could make my rectangles so that the height of the rectangle lines up with the left-hand side, right? So this is your f of x. This is a left-handed sum. And your book likes to call it a lower sum, right? It's not called a lower sum because it's always an underestimate. Sometimes a lower sum is an overestimate. Then you could also do a right-handed rectangle, right? So that the height of the rectangle is on the right side of the rectangle, right? So this is a right-handed sum. Or upper sum. Right? So it's usually either called a right-handed sum or an upper sum. You don't have to say the whole thing. And then there's a midpoint, right? Where, and this one's actually a better estimate, but it takes a little bit more work. You'll notice as the function passes through, if I'm picking the function value to be the midpoint, then what I end up having are these 2 little areas. This part is too little, and this part is an overestimate, and the underestimate, the overestimate and the underestimate cancel out a little bit. So it actually makes it a little bit better, estimate. There's actually some other stuff too. You can estimate areas using trapezoids and things like that, and we'll talk about some of that stuff later. But this one's called a midpoint. This is computing the area using, I don't know why they call it a rule, but the midpoint rule. Okay, so those are the 3 different ways we can decide the heights of the rectangles, and we're going to go through all 3 of these ways. And so let's go ahead and get started. Oops, I don't want to do that way. Let's go back. There we go. Let's just do this. There we go. Sorry, I'm muttering to myself like a crazy person. All right. Now I'm going to overdraw this picture so we can really have a good sense of what we're looking at here. So this thing's going to cross at 1, and it's a parabola, so it's doing this, right? It's going up somehow. I know it goes to the left too, but the area I'm looking at starts at 0. So I really only care about this thing between 0 and 2. So we'll call this 2. And this is not a drawing to scale by any means. All right, so first, let's go ahead and estimate this using a right-handed rule. Now, your homework will tell you how many rectangles to use. As you go through your homework, it's either going to tell you to use 2 rectangles or to use 4 rectangles. It could be any number of rectangles, but they're being very specific so that your answer matches. So we're going to compute this as a right-hand rule. So that means we're going to have to divide this Oh, I forgot to write n equals 4. So there's 4 rectangles. So that means we need to divide this into 4 pieces. So that would be 1, this would be 1/2, and this would be 3/2. Now, so let's draw in our rectangles. Let's figure out, it's a right-handed rule, so that means the right-hand side of each rectangle is what's going to be the height of the rectangle. And we can tell just from this that my drawing isn't to scale. But let's see here. So this is one rectangle, and then this is another, and then this is another. And and then the last one would be way up here. I actually forgot about that guy. This guy would be way over here. So we have to take it all the way to the edge. So the idea here is just to compute the area of each rectangle, right? Now, when it comes to your x values, your evaluation points, and these are your x values that you're plugging into the function, right? So what we're going to be looking at first is, well, we need a height times a width. Now the width is our delta x, right? And that's b minus a over n. Well, b and a are here, right? That's a and that's b. So this is 2 minus 0 over 4, which is 1/2. So that means the width of all of our rectangles is 1/2. We can just keep reusing it. We don't have to recompute it each time. And our evaluation points are at 1/2, 1, 3/2, and 2. Those are the right-hand side of each one of those rectangles. So I'm going to label these areas this way. This is area 1, area 2, area 3, area 4. And let's compute them. So area 1 is going to be the height of the rectangle, which would be, let's see, that the evaluation point's at 1/2, so this is going to be f of 1/2 times our delta x, which is 1/2. And I just want to point out to you that this is AI is equal to f of xi times delta x, right? That's really what we're looking at here. So as soon as we have our xi's, the formula is there. We're just going to keep reusing it over and over and over again. So let's see here. And I'm going to do this arithmetic quickly here. If I plug in 1/2 to f, I'm squaring 1/2 and then adding 1. That makes 5/4. And then if I multiply it by 1/2, I get 5/8. So the first area is 5/8. Area 2, you can see how this can get very tedious when you have like 10 rectangles, would be f of 1 times 1/2. F of 1, 1 squared plus 1 is 2, half of 2 is 1. In fact, let me do this, just so they stand out a little more. That's 1. A3 is f of 3/2 times 1/2. And if you plug in 3/2 into f, you square it, you get 9/4. Plus 1 makes 13/4. Times 1/2 makes 13/8. And then A4, which would be the last, let's see, that we're x4, so that's 2. So it's f of 2 times 1/2. F of 2, that'd be 4 plus 1 is 5, times 1/2 is 5/2. And if you go ahead and just find a common denominator here and add everybody together, oh, I see what I was looking at. Yeah, that comes out to 46/8 or 23/4. Sorry, I'm getting distracted by writing this and trying to talk at the same time. So that comes out to 23/4, right? And that's our estimate. So the estimate of the area is 23/4. And now you want to think about, is this an overestimate or an underestimate? And you can tell most of the time by just looking at your picture. If you look at your picture, all of those rectangles are bigger than the area they're covering. So this is an overestimate. Right? And I will tell you, let's see, where did I put it? I computed the actual area. It actually turns out the actual area is 14 thirds, which is 4 2/3. Just to give you an idea. This is over that, right? Because this is 5 3/4. Right? So this is a way of checking. Now, the way I came up with the actual area is something we're going to be covering in the next couple sections. So we will see that very soon. And just like with derivatives, we're going to have this clunky, hard to work with definition, which is actually it's important because I can tell you I have used this many, many times to be able to find what I'm looking for in the integral. We're going to go through this clunky kind of way to do it, and then we're going to, well, honestly, we're going to take a limit and we're going to turn it into a nice method that we can just compute algebraically instead of having to go through all this arithmetic. All right, so that is a right-handed rule, a right-handed estimate as far as this goes. This is an upper estimate. Again, it's not called an upper estimate because it's an overestimate. It's called an upper estimate because of the two endpoints that you could use to evaluate this, we're using the upper endpoint. Okay, so that's a right-handed rule. Now let's go ahead and take a look at a left-handed rule. Let's see here. I want to do that. Well, let's get this off of here. Okay, that'll work. And then we can just clean it up this way. All right, and then let's go ahead and get rid of some of this. I'm going to try to reuse my picture. I don't know if this is going to work out or not. We'll find out here shortly. Okay. That is not a pen. There we go. All right. Now, if we are going to do a left estimate, what that means is that we are now going to switch the side of the rectangle we're using from evaluations. Before we were using this height, now we're going to be using this height. So this one's actually going to be a little smaller. Right? This is going to be a bit of an underestimate. Right? You notice all the rectangles are a little bit less in area than the actual area under the curve. So again, we're going to do the same thing. But you notice we're going to have different evaluation points this time. Because it's on the left-hand side, we're going to start with x1 being 0. So now our evaluation points are here. Right? You notice I'm leaving the 2 alone this time. So again, a1 is going to be f of 0 times 1/2. Right? That's the height, that's the width. Notice delta x doesn't change for any of these methods. It's always 1/2. A2 is going to be f of 1/2 times 1/2. A3 is going to be f of 3/2 times 1/2. And A4 is going to be f of, oh, I got ahead of myself. Sorry. I started thinking about the other example. That's f of 1. Sorry, that's the third, f3, or x3. And so f4 is 3/2. There we go. Times 1/2. And these are going to compute pretty much the same way. You plug the value into f, figure out what you have, and then multiply it by 1/2. And so we're going to get these values. 1/2, because this is 1 times 1/2. Here, f of 1/2, we actually computed that last time. We end up with 5/8, and then this one ends up being 1, and this one ends up being 13/8. And if we add all these areas together, that. Try that one more time. Right? We add all those fractions together, we end up with 15/4. Now this should be an underestimate because we have all these areas over here that didn't get counted. These are all the things that didn't get used, right? That those areas aren't counted. So this should be an underestimate. And remembering that our actual measurement was 4 2/3, if I look at this ends up being let's see, 3 3/4, right? So this is 3 3/4. So this is an underestimate. Now, keep in mind, too, you're going to be plugging most of these numbers into a calculator. You're going to be getting decimals. I like to work with fractions just because I can do them in my head and I don't have to turn to a calculator. That's basically the idea. Okay, so we got our first two estimates, right? And we know for a fact that the actual area, well, we know what the actual area is. I already told you. But we know that the actual area is sandwiched somewhere between 3 3/4 and 5 3/4, right, from our two estimates. So you can actually sandwich down the area a little bit. All right, so let's take a look at the midpoint rule, which is the last one we want to get. And then I want to formalize a little bit of this notation in preparation for the next lecture, and then we'll go from there. Okay, so let's go ahead and clear this off. What button do I want? There we go. We'll do that. Okay, so let's go. Oh, I'm just going to redraw this whole picture, I think, just because. All right, sorry I wasted a little time there, but let's go ahead and start drawing. All right. Oops. Let's turn the pen on. What the heck's going on here? Brushes. There. Try it one more time. There we go. I knew I'd figure it out sooner or later. Okay, so once again, well, close enough. Let's say that's 1. We're just going to go ahead and throw this down at 2. And then again, we have 1, 1/2, 3/2. Okay, so the width of, if I'm using the midpoint rule, what that means is that the evaluation point is going to be in the middle of each one of these rectangles. Okay, so that's not the middle. So the rectangles, let me draw in the what we have here. The rectangles are still delineated here, right? The height of the rectangle is decided by the midpoint. So my evaluation points are the midpoints, right? So when I draw in my rectangles, they should straddle across. So they're going to be, the height of these rectangles is now here. And then here. So it's in the middle of each one of these. Sorry, I think I bled over a little bit there. And then here. Probably see it the easiest on the last one. So to figure out what the height of these rectangles are, we need to know what the midpoints are. So first of all, midpoint formula. To find a midpoint between two values, I don't want to use A and B because those are the endpoints. I'll just do that. No, I don't want to use that notation. Let me try that again. Yeah, let's just say between X and Y. Is X plus Y over 2, right? So you just average the two ends. And really, most of the time, you can actually figure this out on your own. But So the first one, the average between 0 and 1/2 is 1/4. So our first evaluation point is at 1/4. Our second one is halfway between 1/2 and 1, which is 3/4. Here, between 1 and 3/2 is 5/4. And lastly, between 3/2 and 2 is 7/4. Notice once you find the first one, you just add 2/4 as you go across. You just keep adding 2 to the numerator. 2/4 is 1/2. So these are all 1/2. These are all delta x apart, and that'll actually become important in the future lectures. So my evaluation points x1, x2, x3, and x4 are the midpoints of each of the intervals that you've divided the rectangles, that you've used to divide up the rectangles. But the formula stays the same. So if this is A1, A2, A3, and A4 that we're finding, A1 is still f of x, or f of x1, 1/4 times delta x. I'm going to erase this because this is going to get in the way. A2 is going to be f of 3/4 times 1/2. There's your delta x again, right? This is f of xi times delta x. You notice the only thing that has changed in any of these is what you're plugging into the function. That's the only thing that's changed. A3 is f of 5/4 times 1/2, and A4 is f of 7/4 times 1/2. Right, so we just need to compute these things. Now these get pretty messy, but you can check your arithmetic and you should get, for the first one, let me switch colors so they stand out here. 17 30-seconds, you can already see it's already messier. 25 30-seconds, 41 30-seconds, and 65 30-seconds. And if you add all those up, it ends up coming out to 148 30-seconds, or excuse me, 148, is that right? Oh, there we go. Yeah, there we go, 74 30-seconds. Sorry, can't read my own notes. And once we boil that down, that's about 6 and, oh, excuse me, 4 5/8, right? Which is very, very close to the actual area for 4 2/3, right? You can see that it really is a much more accurate estimate as far as that goes. Now, in the last video, I actually went into a little bit of foreshadowing, and we've done some of this foreshadowing, but I'm kind of blending it in as we go. But I'm going to go ahead and wrap it up here, and we'll just go ahead and handle those other things in the next videos when I actually introduce them. But some of the things that I talked about is what's called sigma notation, which is a notation when you have to add something up, and it's more or less the same thing you're adding each time, right? Kind of like all of our terms are f of some x times delta x, but we're doing it over and over and over again. And so it's a way of adding up all those sums, adding up that sum in a more compact package, basically. And so you may have seen some of this if you've taken statistics using the capital sigma, which kind of looks like an E. But anyways, the capital sigma is going to be used much more stringently in this class than it's used in a statistics class. It's used very casually in a statistics class. We're going to need to actually use notation very technically. Okay, so wow, somehow I managed to cover almost the same material with 15 minutes less in the video. So anyways, until next time, keep your pencils and your wits sharp.